In an effort to provide mobility for people, not just automobiles, the Florida Department of Transportation has developed planning tools to use for bicycling, walking, and for transit riders. In a world of transportation engineering and design, empirical data is used to drive decisions on what to build and fund. Up until the late 1990s, bicyclists, pedestrians, and buses were not included in those database decisions as there were no objective tools to measure their impact or the likelihood of use. But in 1999, in an effort to bridge the divide between poor land use planning and transportation, the Florida legislature directed the Florida Department of Transportation to develop multimodal level of service assessment tools and a methodology for implementing them. In an unprecedented move, the department chose to ask users of these modes of transportation, as opposed to just experts, what was most important to them. We did this in a scientific manner, and we used their collective responses to develop these level of service models. We took these models and then we integrated them into the automobile level of service methodologies we use in 2002. And since then, they've been used by planners around the state and country.
And level of service is a convenient means of articulating to decision makers and to the public how well a roadway is accommodating the various users of the roadway. For example, motor vehicle users, drivers, bicyclists, pedestrians, transit users. It's essentially a stratification of how well, of a measure as to how well the roadway accommodates the various users.
How many cars can we move down the road at what speed? Those criteria were developed by the professionals who build roadways. What the new trend and level of service, this is bicycle, pedestrian, transit, and motor vehicle, what it is now is going to the users and saying, what makes it a good facility for you?
We usually did this by controlling different variables and having them either riding a course or walking a course. And then ultimately we developed a video simulation method of doing that as well.
For bicyclists or for people walking along a roadway, their perspective of how well a roadway serves them is more from a perspective of how safely or comfortably they're accommodated in the roadway cross-section. And therefore, there's geometric factors, there's traffic operational, there's dimensional factors that all play into that safety and comfort perspective.
The original Ride for Science in 1995 was to determine how safe and comfortable bicyclists feel in certain conditions mid-block. That was the first of numerous projects to do just that. Put real people in the field, measure their perceptions of safety and comfort, and then create models based upon what was going on and where they were walking and bicycling.
In the year 2000, Florida DOT commissioned and sponsored a data collection event called the Walk for Science, and that was held in Pensacola, Florida, and the focus of that research was to get the perspective of people walking along roadways and to be able to quantify how safe or comfortable they felt within roadways, and then to identify then what features of the roadway environment affected pedestrians. That data collection event and the following planning tool development plays a big role now in how roadway cross-sections are designed for accommodating pedestrians. In 2002, Florida DOT commissioned a data collection event called the Ride for Science, and this was based in Orlando, Florida, in which people were asked to bicycle through a number of intersections in that metropolitan area and rate how well those intersections accommodated them.
Well, actually, the Walk for Science is 3 different events or 3 different research projects. We have a Walk for Science for intersections, where we're trying to find out how people are accommodated as they walk through intersections. We also have a Walk for Science for facilities, and the facility consists of the intersection plus the segments of roadway between intersections. And then we have a video simulation Walk for Science, in which we're trying to determine how to calibrate a video from a walker's point of view to real-world experiences, and so that instead of having to put people out on a course everywhere, we can show them a video of local conditions and they can grade it and we can calibrate it back to the field data.
The resulting mathematical model accurately reflects how intersections accommodate pedestrians. The model includes geometric and operational factors.
On Saturday, November 12, 2005, over 60 volunteers gathered at the Museum of Science and Industry in Tampa, Florida, to participate in the 2005 Ride for Science research project. This unique transportation event gathered data from the participants through two activities. The first, while riding their bicycles on a 20-mile course specifically designed to include a variety of urban traffic conditions, and secondly, while viewing a number of video recordings made from a bicycle in similar traffic situations. The volunteers were asked to rate their feelings of safety and comfort by grading selected segments on a scale from A to F.
In finding the correct methodology for the video simulation, we've tried perhaps half a dozen different combinations of bicycle camera mounts. And in doing that, we came up with a recumbent and upright bicycle combination.
This project confirms for the first time that it is possible to use a moving camera or moving video platform to simulate actual bicycling environments. This model includes two major components: the conditions within the roadway segment and the number of conflicts per mile that bicyclists have with motorists from side streets or driveways.
We hosted a two-day workshop in Tampa, Florida in December of 2007 to bring together the practitioners, the people in the field who would be using these level of service models. Transportation planners, engineers, bike ped coordinators, regional planning council staff, those kinds of people. After collecting data on 6 roadway corridors in 3 DOT districts, we videotaped each corridor and then showed it to the participants to give them a visual context of the road characteristics. They were given an Excel spreadsheet of models and data from the 6 selected corridors to look at the interplay between modes, to work with the data, increasing or decreasing various characteristics such as traffic volume, speed, etc. They were asked to react to the interplay between modes and the sensitivity of the models in their ability to reflect level of service for the various modes. Following this exercise, workshop participants discussed the sensitivity of the models, their strengths and weaknesses, and made recommendations regarding their application and implementation strategies for their use.
People found that the sensitivity of the arterial model was different than the sensitivity of the regular segment level of service models. It's much harder to get an A on an arterial road with those models than it is with the segment models. Consequently, they may want to use the segment models on the local or collector roadways. So one of our recommendations was keep the regular bicycle segment level of service model, pedestrian segment level of service model for the locals and collectors, and then provide the option to use the arterial model for the bigger roadways.
It is important that the bicycle and pedestrian level of service consider the types of facilities, how they function, and the surrounding land uses. This attention to context sensitivity challenges many of the tools we currently use for roadway level of service. What is a reasonable pedestrian or bicycle level of service on a collector road or residential street near, for example, a school is very different than what we would accept or expect along a major arterial. The challenge is to create the best design for a specific type of roadway and understand how it affects the level of service for all modes of transportation.
From the workshop, it's clear that there are several models available for determining the bike and pedestrian level of service. Clearly, it's going to be important to identify one primary model which has the most important and relevant explanatory variables for the most general use. And this primary model can then be tweaked using insights from the other methods for more specific applications. A second recommendation from the workshop relates to using the outputs from the model. As you can see, the model produces a numerical score as the primary output, which are then converted into the A through F letter grade. If we were to use the numerical score as the primary output from the model more directly, then we can see a greater sensitivity of the models to the policy-oriented explanatory variables.
Another thing that was discovered or was common feedback at the meeting was that there was no model for a shared use path that was located immediately adjacent to the roadway or very close to a roadway, a side path, if you will. And one of the things that was suggested is that research be done. There's a theoretical construct that's been created, but people wanted research to be done to validate that construct or create an actual model for how safe and comfortable people feel using these side path type facilities.
On Bike Florida's spring event, TrailLink 2008, we surveyed the participants on an assortment of side paths, multi-use trails, shared use pathways, and low-volume country roads to get their perception of comfort, safety, convenience, their use of these particular facilities. We will be using the data to calibrate the theoretical construct and then incorporate that into the bicycle level of service model.
I believe Florida has been at the forefront of this type of research for a number of reasons, one of which I think is that they understand that if something isn't counted, it doesn't really count. And this is a methodology, in a way, to quantify how well bicyclists are being accommodated in the transportation network, how well pedestrians are being accommodated, how well is transit serving people. Florida DOT in particular has made it their mission to be a complete balanced transportation agency, and therefore that includes being able to measure, program, design, analyze, and build facilities for all modes of transportation.
What this means is, ultimately we're trying to satisfy our public, and it could be that we can satisfy our public for a lot less money for the automobile driver and improve the environment for the bicyclist, pedestrian, and bus rider.